Okay, hello everyone. Welcome to our next lecture on 302 course. So today I will continue on talking about Routh method. So let me share my screen. Okay, I hope we can all see my screen now. And in the previous lecture, we were talking about the stability of systems. Right? And we were particularly interested in that given a characteristic equation of a system, let's say d of s, a polynomial, and we want to investigate if the system is stable without explicitly finding the roots of this characteristic equation, but rather instead of finding the pole locations, we would like to work on the coefficients. And for this purpose, we talk about the Routh-Hurwitz method. Routh-Hurwitz method. And in that method, you just construct a rotary, right? We so have to construct that. And then we investigate the first column of that rotary and decide on the stability of the system. And I can simply summarize what we mentioned about the first column. So I will write it over there. Paste here. Okay, so the first rule that we mentioned was that the system is stable if and only if all the elements in the first column of the rotary are positive. So that was the first thing that we mentioned. And the second thing we mentioned was that, right down below, so if there are sign changes in the first column, or if you encounter one of the difficulties that we mentioned before, then the system is unstable. So that was an easy way to check if a system is stable by inspecting the denominator of the transfer function. Okay. So I talked about the first difficulty in the previous lecture. Now today I will talk about the second difficulty. So let me write that thing down. Sorry. Okay. And in second difficulty corresponds to the case where all elements in any row of a rotary are all equal to 0. Okay. And if such a case happens, then it is known that there are roots of equal magnitude lying radially opposite in the S-plane. So maybe I can underline that. So we have equal magnitude and radially opposite roots in the S-plane. So let me try to show possible cases. So let this be our S-plane. And I will show the possible placement of the poles when they are equal magnitude and lying radially opposite in the S-plane. Okay, so one combination can be, so one of the roots might be here and the other one might be just right opposite here. Okay, and as you see, in this case, the system is unstable because of this pole on the right half plane. Or another case can be, you might have one of purely imaginary complex poles, okay, which lies radially opposite in the S-plane. And again, since we have poles on the imaginary axis, the system is again unstable. Or another combination can be, so you might have complex conjugate poles, and you might have poles radially opposite there. And again, we have now 4 poles lying radially opposite in the S-plane, and the system is still unstable because of 2 poles over there. So regardless of the how these poles lay in the S-plane, if we encounter difficulty number 2 or any of the difficulties actually, we conclude that the system is unstable. So I will show you one example and continue, okay? So, example, suppose we have a characteristic polynomial as follows, which is the denominator of a closed loop transfer function. Let it be s cubed plus 2s squared plus s plus 2, okay? And we would like to find if the system is stable or not. So let's start constructing our rotary. I will start from the highest order term here, so which is s cubed, and then write down s squared, s to the power 1, s to the power 0. And I will write down the coefficient of s cubed here, which is equal to 1. So I skip one term and go to the next one. Coefficient of s is equal to 1. I will write down the coefficient of s squared here. I will skip the s term here and write the coefficient of s to the power 0 term over there. If you would like to, you can fill in zeros here and proceed with computing the next row down there. So in the next row, if I would like to compute the first term over here, that will be simply equal to 2 times 1 minus 1 times 2 divided by 2. So that will be simply equal to 0. So let me write that down. And if you would like to compute this term over here, so it should be 2 times 0 minus 1 times 0 divided by 2. So it is again equal to 0. So let me write that here. Okay. And as you see, now we have a problem, because if you would like to proceed to the next row, we will encounter a division by 0 problem. Okay. So we encountered the second difficulty here. We do have a 0 row. Okay. So if we encounter a 0, what we do is, so first of all, we conclude that, maybe I can write it down. So we conclude that the system is unstable. Okay. The system is unstable because we encountered the difficulty. Okay. Then what we do is we go one level up. Okay. So we go one level up. One level up. And we construct a polynomial. Let me write it down like a construct. Let me say the polynomial. P of s. And I will construct this polynomial from the coefficients of the upper row and the s squared term over here. So in this example, P of s is equal to 2 times s squared plus 2. Okay. So what we do next is that we replace the 0 row with the coefficients of P prime of s. So let me write it down. So we replace the 0, place the 0 row with the coefficients of P prime of s. And in our example, P prime of S is the derivative of P of S is equal to 4S. Okay. So I go to the zero row and replace these zero coefficients, zero terms with the coefficients of 4 times S. Okay. So this is the row corresponding to the S term over here. And I will write here 4 instead of 0. Okay. And if I would like to continue filling in the rotary, so if I go to the next row, let me show you. So this term will be equal to 4 times 2 minus 2 times 0 divided by 4. So that will be equal to 2. I can write that down. And now we were able to handle the 0 row and fill our rotary. Okay. And we will still investigate the first column to find the number of poles with positive real parts. Okay, so if our purpose was only to check the stability, the moment we encounter the zero row, we can conclude that the system is unstable. But if we would like to find the number of poles with positive real parts, we will check the first column of the rotary here. Okay. And we will trace the terms from top to bottom. So 1, 2, 4, 2 are all positive numbers. Therefore, there are no sign changes here. So no sign changes here. Which means that no roots with positive real parts. Okay. Real parts. Okay. But the system is unstable. So the system is unstable. Okay. And why it is unstable? Because when we have a 0 row, we have poles lying radially opposite in the S-plane. And if you have poles lying radially opposite in the S-plane, then you have some unstable poles among them. Okay. So I will write here one more fact. So maybe I can write it here. So this polynomial P of S is sometimes called the auxiliary polynomial, is a factor of D of S. Okay, so let me write it down. So P of S is a factor of D of S. Okay. So in some occasions, I can exploit this property to find all roots of D of S, okay? Because if P of S is a factor of D of S, if I perform a polynomial division, so if I divide the D of S by P of S, the remainder should be equal to 0, okay? So this simply indicates that I can write D of S as P of S and some other polynomial Q of S, and the remainder should be equal to 0. Okay. So let's do that and see the poles of this origin polynomial D of S. So I will write D of S here, which was equal to S cubed plus 2S squared plus S plus 2. And I divide it to P of S, which was equal to 2S squared plus 2 in our example, 2S squared plus 2, okay? So I will write here S over 2, then I will get the s cubed term plus s and subtract those guys. I will have 2s squared plus 2 here and plus 1 over there. So let me subtract that. The remainder is going to be equal to 0. Okay. And this way I was able to find the third pole over here. So I can write d of s as 2s squared plus 2 times s over 2 plus 1. Okay. And the corresponding poles are, so from here s1, let's say, is plus j. Okay. And here s2 is equal to minus j. And here, let's say, s3 is equal to minus 2. Okay. So let us plot the pole locations on the S-plane. So, and see the reason for instability. Okay, so let this be our S-plane. So I have one pole at -2 and two poles which are purely imaginary, and they're on the imaginary axis. It's 2 and minus j and plus j. And as you see, since we have poles on the imaginary axis, the system is unstable. And these two poles are radially opposite in the S-plane. Okay. Okay, so let's continue with another example. In our next example, let us consider the polynomial s to the power 4 minus s cubed minus 7s squared plus s plus 6. Okay, let's construct a rotary. So starting from the highest order term s to the power 4 and continuing with s cubed, s squared, s, and s to the power 0 over here. And I will write down the coefficient as the coefficient of s to the power 4 term is equal to 1. Then I will skip 1 and write the coefficient of s squared term, which is equal to -7, and write the term 6 over here. And on the second row, I will start with the coefficient of the s cubed term, which is equal to -1. And then I will skip the next one and write down the coefficient of the s term, which is equal to 1. And you can fill in 0 here if you would like. So let's proceed with computing the next row over here. So if I like to compute this guy, that will be simply equal to -1 times -7 minus 1 divided by -1. So this is equal to 7 minus 6 minus 6. Okay. So this is equal to -6. And if you like to compute this term, or I will show it another. So that term is equal to -1 times 6 minus 1 times 0 divided by -1. So that is simply equal to 6. Okay. So I will write here as 6. Okay. And 0 here. So if I continue to the next row and compute this term, so this will be equal to -6 minus -6 divided by -6, so it will be equal to 0. So let me write it down as 0. Okay, and this term can be computed by multiplying those two and subtracting multiplication of those two, which is 0 minus 0, divided by minus 6, so it is again 0. So this is also 0. Okay. And we do have a 0 here. Okay, so 0. Okay. So when we encounter a 0, what we do is to go one level up and construct our auxiliary polynomial. So I will construct the auxiliary polynomial P of S as from the coefficients of the upper row over here, which is equal to minus 6s squared plus 6. Okay. And I will replace the 0 with the coefficient of the derivative of this polynomial. So I will compute P prime of S, which is equal to minus 12s, and replace the coefficients of the 0 with the coefficients of this polynomial, P prime of S. So let's do that. So instead of 0, I will write minus 12. Okay. So this would be minus 12. Okay. And if you compute this term, you're going to multiply those two numbers and you multiply minus 6 by 0, subtract from that number and divide by minus 12. So this will be equal to 6 as well. Okay. And since I finished constructing my rotary, I can now inspect the first column. Okay, so I will inspect the first column just to see the number of sign chains and inspect the number of roots with positive real parts. Okay, I already know, since I encountered the 0, some of the poles are either on the imaginary axis or on the right half plane. Okay, so the system is unstable. But let's say we would like to find out how many poles have positive real parts. So I will inspect these sign changes and I will then trace the first column from top to bottom. So when I'm going from 1 to minus 1, there is one sign change here. Okay. When I'm going minus 1 to minus 6, there are no sign changes. They're both negative. When I'm going from minus 6 to minus 12, there are no sign change. They're both negative numbers. But when I'm going from minus 12 to plus 6, there's another sign change. Okay. So another sign change happened here. So I do have two sign changes. And I will conclude that two roots, let's say, two roots of this polynomial have positive real parts. Okay. And I know that the P of S is a factor of this polynomial D of S. Okay. And the poles corresponding to this term over here, they lay radially opposite in the S-plane. And one of the poles is, as you see, plus 1. And the other one is equal to minus 1. Okay. So I already know that when I encounter the 0, the roots don't lie on the open left half plane. So if this was a characteristic polynomial of the system was unstable. And I also know that there are two sign chains in the first column of the rotary. So I know that there are two roots with positive real parts. Okay, so that's how we deal with the 0 rows in the rotary. So let's continue with another example.